Welcome, everyone. We're very excited to have you here for NESE's final pre-conference webinar for our Building Energy NYC conference. We have Jon Hacker with us here today from Daikin, one of our conference sponsors, here to talk about heat pump inverters. Very exciting content. We're glad to have you with us, and we hope to see many of you next week at the Building Energy NYC conference in person on Thursday the 15th. If you have not yet registered, I'm going to put the registration link here in the chat. Just a note that pricing is going to go up on Monday at 5 o'clock by $50, so make sure to register before then. Please feel free to introduce yourselves in the chat so we know who's here. You can also post questions along the way. Jon will respond to those at the end of the presentation. And with that, I will hand it over to Jon.
Thank you, Ben. Good afternoon, everyone. Thank you for joining me today. I'm going to share my screen and get started here. I hope you're looking at my slides. I believe I'm sharing the right
yes.
the right screen here. Thank you, Ben. I appreciate you confirming that. So good afternoon to you all again. I want to thank NESE for allowing me to present today as the final pre-conference webinar as we build up to Building Energy NYC next week. I am Jon Hacker with Daikin US, where I am the Director of Decarbonization and Energy Efficiency. The previous pre-conference webinar was from NYSERDA and highlighted their efforts on community thermal networks, which is a new way to decarbonize buildings using existing technologies like heat pumps. As a continuation on that theme, I want to take a good chunk of time today and over the next 30 to 40 minutes, talk about inverter technology, which is critical to allowing us to leverage heat pumps as a sole source of heat for buildings in the Northeast. As Ben suggested, I see some folks introducing themselves. That's great. I see some familiar names. I see some new names, which is fantastic. And as we go, I'm going to try my best to answer some questions as we're kind of on those topics. So as we go, please feel free to put your questions in. I am a one-man show today. I'll do my best to get to them. But I certainly reserve some time at that end for questions as well. So this is a quick rundown of kind of some of the content and topics I hope to talk about today. I'll give you a quick introduction to Daikin, who we are and what we do. I'm going to talk about inverter and mechanical system basics. Some of you guys will find that content a little fundamental, but I want to make sure we all have a common knowledge on some of the topics before I really dive into the impact on mechanical system operations with inverter, right? It's going to be a little more technical. We're going to look at a lot of graphs and figures there, and really, I think, dive into the meat on why inverters are so important. And then I'm going to summarize some of the benefits to society and occupants and energy consumption from inverters. And then lastly, show some examples of what really happens when we apply them. So with that, I'm going to dive right into talking about Daikin a little bit. Daikin's coming up on their 100-year anniversary, which we'll celebrate in 2 years. We have sales roughly on the order of magnitude of $20 billion annually across the globe, of which about a quarter of those comes from the United States. And we're really a global business. We have sales and operations in almost every country across the globe and an enormous amount of localized production bases. So what that means for the United States is we operate production facilities in Texas, Minnesota, Virginia, among others, to name a few. Daikin is somewhat differentiated and unique in the sense that we're really just focused on HVAC solutions. More than 90% of our sales come from that. And it really allows us to focus on providing the best solutions and putting them into the marketplace. And with that, we like to think we have 3 core competencies. The first being heat pump technology, which I'll talk about in a little bit. inverters, which we're going to spend what hopefully is the whole time today talking about. And then lastly, refrigerant or refrigerant control. Just a plug, Daikin will be participating in 2 separate sessions during Building Energy NYC. Both are in the afternoon, and both will mostly focus on refrigerants. I know that's a hot topic and very important, and we want to make sure we're putting that information out there and able to engage with the community on those topics. So Daikin is kind of represents the global company, but in the United States and North America, we represent a number of different brands that put a number of different solutions into the marketplace. So with that, we our solutions carry the brands Daikin, Goodman, and Amana, and those comfort solutions kind of come in a number of different forms, from a small single mini split configuration, which may be appropriate for a single room, and ranges all the way up to central plant chillers, which could provide comfort cooling for hospitals or campuses. And we provide a number of solutions in between, including rooftop units and our flagship product, VRV, which is a kind of light commercial modular heat pump system, which could be used in smaller to large commercial buildings as well. And Daikin's established a goal of being net zero greenhouse gas emissions by 2050, many years before it was fashionable. And we have a plan to articulate how we will achieve that goal, which is through our products, through better solutions, and by leveraging the power of air, by advancing technologies and meeting the changing needs, of individuals and organizations across the globe. So our plan outlines how we'll achieve a 30% reduction in greenhouse gas emissions below our business as usual case by 2025. These goals are challenging to hit as they include emissions from producing our equipment and all of our operations, but also the emissions of operating the equipment through its end of life. So many of our emission reductions will come from products that are higher efficiency and decarbonizing heating systems, solutions that improve the operation and use of our HVAC equipment, and ultimately the development and deployment of more environmentally refrigerants and improved refrigerant management practices. So moving on to kind of the mechanical system and inverter basics, I think a wonderful place to start is just to kind of put the question out there: what is an inverter? And to put it simply, it's really just a small little circuit on a printed circuit board with that serves the function of changing the frequency of the electric signal that we get from the utility. So in North America, the electric utility provides electricity at 60 hertz. In other parts of the world, that might be 50 hertz. And that has an impact on the operation of the compressor, which is the core piece of an HVAC piece of equipment. And all an inverter does is allow us to change the frequency of the electricity supplied to the compressor. And that'll have some really impactful, meaningful changes to how our equipment operates, and we'll go through those in a lot of detail. During the discussion today, I might refer to the equipment as variable capacity. I might refer to it as inverter driven. There are a lot of different names that you can call this. And ultimately, some of you may be familiar with NEEP's cold climate air source heat pump list, which is used as a prerequisite for heat pumps to participate in rebate programs in New York. Inverters or variable capacity functionality is a requirement for heat pumps to participate in those programs. So others may refer to this technology as cold climate air source heat pumps. So I told you what an inverter does. It changes the frequency, but really, what does that mean, right? And I like to draw the analogy to a car. It's something that I think many of us are familiar with and have experience being in a motor vehicle. And traditional HVAC equipment, whether it's single stage or two stage, operates in a very simple nature. It is either on or it's off. And this would kind of be like driving a car that's got a push button, right? When you're pushing that button, the motor is basically running at full speed. You got the pedal to the metal. And when you're not pressing that button, it's kind of just coasting, right? And if you think about driving in a car that doesn't have a gas pedal, but instead is a button and the motor is either all the way on or all the way off, you know, it's going to be pretty uncomfortable to ride in. You might get whiplash. It's also a very inefficient way to drive. You're going to waste a lot of gas, and you're also going to exert a lot of extra wear and tear on the components of that vehicle. They're going to wear out quicker because you're exerting more force than necessary. So taking that same analogy, a car, and thinking about an inverter, it's really like a gas pedal. You can now kind of change how much acceleration you want. It's no longer on off, but you can vary that gas pedal to get precisely the speed for a vehicle, or for HVAC equipment, the comfort or capacity that's needed, right? And by allowing that precise control, you're going to be much more comfortable. You're going to be operating that equipment much more efficiently. And it's also, because of the gentle operation, it's also going to last longer. So this might be really basic for some folks, but I do want to talk about just really briefly kind of how a heat pump operates, how it's a little different than an air conditioner, and then I'll even go into some of the components of that. You know, basically a heat pump is a lot like an air conditioner. I think that's something most of us, if not all of us, are familiar with. You know, basically the role of an air conditioner is to move heat, or really reject heat from the space that you're in to the outside to make it more comfortable, right? And that's kind of what I'm showing here in the cooling mode depiction. You've got an indoor unit that is capturing heat from inside that space. It's connected to an outdoor unit via refrigerant piping, and that outdoor unit is rejecting the heat from that system and space. That's why if you stand in front of an air conditioner, you got hot air blowing on you. That's the heat from the space, and it's what makes it comfortable inside. A heat pump works pretty much under the same principles, but in reverse. So instead of rejecting heat from inside, capturing heat from inside, moving it outside, we're actually capturing heat from the outside, even when it's cold out. And it's hard to imagine, but at 0F or -10F, there's an abundance of heat to be captured in that air. Heat pump's going to capture that air, and it's going to move it inside via those refrigerant connections and reject that heat into the space to maintain comfort. Susan asked a really interesting question about what occurs when the heat pump reaches the temperature set point or goal. Susan, I'm going to ask you to hold on. I think we're going to get there. And if you require more information or better explanation, feel free to chime back in at that point. But thank you for your question. I'm showing a basic diagram here of the main components of a heat pump system. The inverter itself, as we've discussed, it's applied on the compressors, and that's because the compressor is the main energy consuming device, and it's really doing all of the work to complete a refrigeration cycle. Item number 2 is the reversing valve, and that's really the only main difference that exists between an air conditioner and a heat pump. It simply reroutes the refrigerant depending on if the system is in heating mode or cooling mode, and by changing the routing, you're going to be able to reject heat into the space or reject heat outside, thus providing heating or cooling. And in addition to the inverter, the electronic expansion valve is a key component which enables a variable speed compressor to precisely modulate the amount of heating or cooling delivered. And they work together to regulate the flow of refrigerant based on the system operational parameters. I do want to point out that heat pumps are new. I think this is a fun way to do it. You know, these are some advertisements from GE from the 70s advertising heat pumps. And the reality is heat pumps are really popular in different parts of the country, right? Maybe historically not so much in the Northeast or New England, but in the southern states and across the globe where climate is milder, they've been used for many, many decades. And, you know, looking back on the Northeast's experience with heat pumps, you know, they don't always have the best reputation, as they didn't always perform well in cold temperatures. And I'd suggest that the differentiator there is the inverter, right? So heat pumps aren't new, but the inverters are. And, you know, for the past few years, we've been able to apply inverters to residentially sized systems more affordably, which allows them to be deployed more broadly and cost effectively in cold climates, thus providing a pathway to decarbonizing our buildings and our homes. And just to give you a sense of inverter adoption across the globe, there's a tremendous amount of opportunity in the United States and North America. So this graphic here shows inverter adoption rates across the globe, with the kind of size of the bar representing the number of HVAC products sold in those markets, and then the green portion representing inverter products, and the blue portion representing non-inverter products. And what we see here is in different markets like Japan, where all HVAC products come with inverters, or in China or Europe, where more than 3/4 of HVAC products come with inverters. Comparing to that, what's happening in North America right now shows a big gap. So in 2018, which is the most recent data that I'm showing here, 16% of HVAC products had inverters. I'd suggest maybe that's crept up a little over the past 4 years, but we significantly lag other parts of the world, and frankly, there's a lot of room for inverters to be used more broadly, and they provide benefits both for air conditioners and heat pumps, and we'll talk about those in the next section. So that was a pretty natural segment there, segue, excuse me. So this is kind of where we're going to get into the nuts and bolts a little bit. I'm going to show a lot of tables and graphs. I like John's suggestion in the chat about requiring inverters. I think there'd be a ton of benefits to be had by that, so I'm going to highlight them now. But great suggestion, John. I'm going to show a couple of different tables and graphs here. This is kind of dry content. I'm going to do my best to really emphasize the key takeaways and points and benefits from inverters. So I've got two different graphs here. They're on the same scale and showing the axes are the same. So on the x-axis, we're showing outdoor air temperature, and on the y-axis, we're showing the capacity of the heat pump. And on the left side of this graph, we're showing a single speed, centrally ducted, 16 SEER, 3.5 ton heat pump. It's a lot of words to describe a HVAC system. But what's important to show here, I think, are two things. One is that we have a cycling line. That's our line in blue. And what we're showing here is that a single speed heat pump can only provide one capacity at any given outdoor condition. So, looking at this graphic, if I look at the 47-degree outdoor temperature condition, that heat pump can provide 40,000 BTUs of heat, and that's it. So it will provide comfort by turning on and off to maintain comfort, but it can only do one thing, and that's provide 40,000 BTUs at that condition. The other thing that you'll notice, which will be important later on as we drive down to applications, is that that line, the heat pump's ability to deliver heat, does diminish as the temperature decreases, right? And that's important. Moving over to the right-hand side of this slide, I'm showing a very similar product. It's also a 3.5 ton product. It's also a centrally ducted product, but this is a heat pump with an inverter. And we no longer have a cycling line, but we have a modulating zone. That zone is showed in gray. And it's kind of defined by the bounds of the maximum capacity, which are shown by some green dots towards the top of that gray box, and the minimum capacity, which is bound by the red dots at the bottom of the box. And the change from a cycling line to a modulating zone cannot be overemphasized. This has enormous impacts to the operation of the equipment, how it provides comfort, and its efficiency. So, taking that same condition, 47 degrees Fahrenheit outside, the inverter product can deliver 40,000 BTUs, but it can also deliver up to 70,000 BTUs or down to maybe 12,000 BTUs. So with that, we now can provide a range of capacities, actually a wide range of capacities at that condition, which means we can modulate the capacity to precisely meet the needs of that equipment. We've got a question about what is the COP while modulating? It's a really great question. I've got some graphics to cover that, but basically the idea is that COP will vary depending on the speed of the compressor, right? So if typically, if we're operating at a slower speed, generally COPs are going to increase at that same outdoor condition than if we operate a compressor at a higher speed, right? So moving on a bit, we've shown okay, we've gone from a cycling line to being able to deliver one capacity at one condition to now being able to provide a broad array of capacities at that same condition. The other really enormous benefit to applying an inverter to a heat pump system, or really a heat pump system, is that it allows that same system to deliver more heat, specifically when it's cold out. So this is what we're showing graphically here. So we've got the same modulating zone, same exact equipment that I showed before, the same blue line for the cycling line for that 3.5 ton piece of equipment. They're just overlaid on the same graph here. And the point I want to drive home is that 3.5 ton product, that single speed, when it's 5 degrees outside, it looks like maybe it can deliver 20,000 BTUs and that's it. But by adding an inverter to our system, we can significantly increase the amount of heat that can be delivered when it's cold out. So if you look at that 5-degree condition for the inverter product, it can deliver in excess of 40,000 BTUs, so more than twice the heat when it's cold out. And that's really important, and that's what's allowed us to use combined inverters with heat pumps and using them in the Northeast for when it's cold out. As just a point of comparison, I've also added a 5-ton system that's cycling, and comparing it to the capacity of 5 degrees Fahrenheit for the 3.5 ton, it can even provide more heat than that. So I think maybe this might address Susan's question, or if this slide doesn't, maybe the next few will. But this is really showing, this is a simplified take, and I'll show a more complex take on the next 2 slides on what happens with an inverter and some of the impacts to temperature, and then specifically on the next few slides, kind of operationally what's happening within the heat pump. So really what this is showing is it's comparing the single speed equipment in a green line and an inverter system with a blue line. And basically what we're showing here is that a traditional single speed system will fluctuate significantly more from the set point than an inverter system, right? So with an inverter system, as it approaches that set point, it can modulate and slow down and more precisely control the delivery of heating or cooling so that it does a better job of maintaining comfort. Where the non-inverter system, it can only operate on or off. So it's going to operate on, it's going to overshoot set point, it's going to turn off, the temperature's going to drift further away from set point until it's kicked on again, right? So we have a much better temperature control with an inverter. So to kind of show that more in the real world, what does that mean for the operation of the equipment? We've got 2 different examples here, and this is data that we've collected comparing a non-inverter unit on the top of the slide to an inverter product on the bottom of the slide. And the color coding is pretty much the same for these 2 graphics. So the yellow is the outlet temperature, the orange line is the room temperature, and the blue lines on both of these graphs are the frequency. And on the left-hand y-axis is degrees, and the right-hand y-axis is hertz for the compressor frequency measurement. And I'm going to take some time to kind of walk through this and explain what's happening. So looking at the non-inverter unit, you'll notice, I think the first thing we need to call out is that the frequency of the compressor is either operating at 0 or 60 hertz. It's either on or it's off. I think that's abundantly clear. So what we see over this 4-hour period is that the compressor for the non-inverter unit turns on and off 19 times. The other thing that we'll see is that when the equipment is on, it will try to satisfy the set point, and then it will cycle off. And when it cycles off, the room temperature, that orange line, will deviate significantly from the set point, which is shown as the smaller dashed line for this example at 73 degrees Fahrenheit. What we're showing on the bottom half of this slide is the inverter unit is a totally different operation. I think it's very obvious it looks different. And we're going to focus on the blue line first again. When you initially power that unit on, you'll see that the frequency is spinning well above 60 hertz. It's actually going up to close to 120 hertz, right? And then as the orange line approaches the set point, the unit begins to try to modulate its capacity and delivery of heat to find the optimal operating condition for the system. So it begins modulating the frequency, and as it's doing that, it kind of starts and stops a little bit. But ultimately, after 2 or 3 hours, what you'll notice is it really just starts making small adjustments to maintain comfort. And what you'll see on the inverter unit is that orange line is, basically fixed on that set point. Doesn't really deviate a whole bunch from it. And that's kind of a good example of how we're providing better comfort with an inverter product than a single speed on and off. You could see, switching back to the top of this graph, when that compressor turns off, the room temperature, that orange line, deviates pretty significantly, pretty quickly from the set point, right? We're just not getting that from inverter equipment. And basically, we get savings from reducing the speed of the compressor. So over time, as that system learns how to precisely match the set point, it can operate more efficiently, we get energy savings. So, we're kind of layering topics now. I've kind of shown some, how we move from a cycling line to a modulating zone. And now I want to show what this really means for like an application. So this is an example home in Westchester, New York. And, again, similar graphic, we're showing outdoor temperature and capacities or loads on the y-axis, loads and capacities on the y-axis and outdoor temperatures on the x-axis. On the left-hand side of the slide, we're showing a single speed product. It's the same exact single speed product with the same exact capacity line, but it's shown in red now. And the example house load that we've got is shown as a purple line. And the design condition for this location is 9 degrees Fahrenheit. And you can see that the heat load line basically goes to 0 around 62 degrees Fahrenheit. So at that point, you don't really need heat anymore. And on the left-hand side of this slide, there's a couple of important things to understand and consider. Firstly, when the capacity of the heat pump, which is shown in red, is higher than the load line, which is purple, that means that the heat pump can satisfy comfort and provide enough heat to keep the occupants comfortable. When that is reversed, when the red line is below the purple line, that heat pump cannot provide enough heat to maintain comfort and will need another source of heat. It could be electric resistance, it could be fossil fuel, but to maintain comfort, we're going to need to inject more heat. And because a single speed product is challenged to provide enough capacity when it's cold outside, in this example, we need supplemental heat. And then basically when the heat pump can satisfy comfort, we have cycling. Again, the equipment can't modulate, it can only turn on and off. So we've got, what I'd suggest is healthy cycling till around maybe 48 degrees Fahrenheit. But then at that point, kind of the ratio of heating needed to maintain comfort, which is the purple line, to the capacity of the equipment in red, there's a big order of magnitude difference there around 47, 48 F, right? That equipment can provide 4 times as much heat than what's actually needed. So that means that when it's that temperature outside, just below 50 degrees, that equipment will operate about 1/4 of the time per hour, right? So maybe 15 minutes out of every hour, but it may operate for 5 minutes 3 times over an hour, right? And that's short cycling, and that's a very inefficient way to operate the equipment. Shifting over to the right-hand side of the slide, showing the same heating load line in purple. We're showing the same product that we showed before, but the modulating zone. And basically what we're showing here is we're kind of bringing all these concepts together, right? With the inverter, we can now provide 100% of the heating that this home would need because the inverter allows the delivery of more heat when it's cold outside. And we're also, we're not cycling, starting around 23 or 24 degrees Fahrenheit, but instead we're modulating and we're operating more efficiently all the way down to, maybe 46 degrees Fahrenheit outside, in which point the load drops below the minimum for this product, and we would have some cycling. And again, we'll have some healthy cycling, maybe down to around 58 degrees Fahrenheit. And we'll have, some short period of time, maybe between 58 and 62 degrees, where we'll have some short cycling. So over the season of the equipment, it's going to operate much more efficiently. And I want to call attention to the difference between design temperatures and really, how those are used and applied and the impact on the operation, right? So talked about the design temperature for Westchester being 9 degrees Fahrenheit. That's actually the 99.6% design temperature for heating for that location. So that means 0.4% of the hours of the year, or about 35 hours, will be below that temperature, which is very rare. If you're looking at this graphic, there are not a lot of hours in the year below 10 degrees Fahrenheit outside. Mechanical contractors and design firms will size HVAC systems for these extreme conditions. They kind of have to. That's the engineering practice. But the reality is that the majority of the time these systems operate, they're not operating at that high of a load. We saw that load diminishes as we get to more mild conditions, right? So in Westchester during the heating season, more than 80% of the hours are above 30 degrees Fahrenheit outside, right? And that's when an inverter system is going to provide the most benefit, both in terms of comfort, but also efficiency, because it's not operating at 100% load, but it's operating at part load. And the same is true for cooling, right? So we design and size the equipment for 90 degrees Fahrenheit, but a large majority of the cooling season, it's not that warm and loads aren't that high, right? So again, and kind of where a lot of those cooling season hours are, 80 degrees and below, the equipment can modulate, provide comfort, and operate more efficiently. So, I was kind of talking about it in the last slide a little bit, but inverter efficiency improves at lower loads, and the efficiency actually exceeds its full load efficiency, or 100% load efficiency. So you can see here, single speed equipment efficiency kind of peaks at full load and gradually falls off. I don't entirely agree with the graphic here that the efficiency goes to zero, but I do agree with the overall trend that it does fall as load is reduced because the equipment will cycle on short cycle. But for inverter equipment, the efficiency increases as load reduces. So, it's drawn back to that analogy with your car, right? If you're cruising on the highway at 60, you're going to get a much higher miles per gallon or efficiency than if you're driving 90, right? And it's kind of the same comparison there. And again, that range of when the load is 75 to 25% is really where the equipment's going to spend a majority of its time. I think I was kind of showing that on the last slide. And EER is an efficiency metric for HVAC equipment, and it's used to describe system efficiency at peak cooling loads at the 100% load level, right? So historically, EER has been the main efficiency metric for HVAC equipment. However, recently there's been a shift to seasonal efficiency metrics like SEER. So SEER does a better job of estimating HVAC system performance over the entire cooling season. Which, in my opinion, I think a lot of other folks' opinion, it's more important than a simple peak load efficiency metric, right? And on the heating side, the same would be true when comparing HSPF, which is the heating seasonal performance factor, to, a metric like coefficient of performance at 5F, which is very similar to EER, but for heating. So there's a number of benefits that are provided by inverters. I think we covered a lot of them. I think the reality is, just to kind of try to summarize, inverters allow the equipment to operate at higher efficiency in part load conditions and thus provide better seasonal performance. And they do a better job of maintaining comfort by throttling the system down as it approaches its set point. So moving on to the benefits to society here, I think we've talked about this already. Inverters provide better levels of comfort, right? This is just a fun way to represent that, but we have smaller temperature swings and ultimately increased levels of comfort when systems are using inverters. This one is interesting. I'm going to take a couple of minutes to try to walk through this, but basically the idea is that inverter systems or variable capacity systems can do a better job of maintaining comfortable levels of humidity. And humidity has a important impact on comfort. All right, so there's a very typical problem with HVAC equipment. Maybe it's a cooling system and maybe it's oversized and it will short cycle significantly. And when air conditioning equipment short cycles, it doesn't appropriately remove the relative humidity in the air. It does drop the temperature, but it doesn't drop the relative humidity. And in that scenario that we're showing here, the room temperature, maybe the set point 77 degrees, but if that equipment is oversized and it's short cycling, relative humidity may stay at 80%. And at that temperature, 80% relative humidity, most humans are going to be pretty uncomfortable. But with an inverter, because it can modulate its capacity, it won't short cycle. It will run for a longer period of time and do a better job of extracting and removing the humidity. You can have the same 77 degrees inside, but with 50% relative humidity and be able to maintain comfort better, right? So it's another way that we can provide better comfort. On the sound side, for me, I think this is the most impactful. About 18 months ago, I installed an inverter heat pump in my home. And if you have a centrally ducted system, if you have any non-inverter product, you'll probably be familiar with the loud thud and bang and sound that you hear when the system turns on and operates. So when you add an inverter to the system, it starts much softer. So you kind of remove that electric surge and that sound and the stress on the system and the pipes. And the system really just becomes less noticeable in terms of a sound difference. I do want to point out that the order of magnitude and the difference of decibels here, I don't think it necessarily does this justice, and it's because the decibel scale is kind of logarithmic. So, even though these maybe are only 20% difference or something like that, it's orders of magnitude quieter. John's asked a question about relative humidity, about pulling out as much humidity as a dehumidifier. I think at the end of the day, that extraction rate is probably going to depend on a number of different factors. The reality is, and this is true for different Daikin systems as well, but a dehumidifier operates on the principle, it uses a set point of relative humidity, so the control parameter is different. Some heat pump systems and some Daikin systems, you can do that. So there is a dehumidify function. So if that's important, make sure you seek out that appropriate model. But I think generally you're right, dehumidifiers serve a different purpose. They're designed to extract humidity from the air and not necessarily provide comfort. So you're probably right in terms of the stats. I think my point was really not in the scenario where you need a dehumidifier, but where an AC system may be oversized and you're experiencing discomfort issues. So I wanted to just highlight some of the solutions that we're putting into the marketplace today that we've seen a lot of adoption with, specifically through the Clean Heat program in New York, and that contractors have really kind of circled around in terms of being great products for this market because they do a good job of maintaining their heat capacity when it's cold outside and operating really efficiently. So I'm showing two different lines here. On the top left, I'm showing our Aurora cold climate air source heat pump. I think almost every configuration of this is on NEEP's list. It's available in a single mini 1-to-1 configuration, in a 2, 3, or 4 zone multi-split as well. And as I suggested, they can provide 100% of their rated heating capacity to 5 degrees and provide continuous heating operation down to -13 Fahrenheit. And those are, kind of more of a ductless product. Again, can be multi-zone. We do offer some kind of low static short run ducted configurations for that as well. And then on the bottom left, I'm showing our Sky Air product, which is a traditional centrally ducted system with an inverter, and that provides continuous operation down to -4 degrees Fahrenheit outside. Does an incredible job of maintaining heating capacity all the way down to -4. And both of these, depending on the application, have become really popular in and around New York City. I'd suggest the Sky Air is really used when there's existing ductwork in the home for retrofit application, or in a new construction when there's going to be centrally ducting available, or the Aurora is used really for a retrofit. Maybe you have a boiler in place, no central ducting. It's a great solution for that. If you need longer line lengths for multifamily application, at that point, you might want to start thinking about the VRV line of products, either single phase electric or triple phase electric as well. So, I think that kind of summarizes a lot of the benefits. At the end of the day, when you get a variable capacity heat pump system, I think you're getting more than just comfort, right? You're getting a solution that's engineered and manufactured to ensure performance, reliability, and efficiency. And the increased efficiency in operation of the inverter system reduces wear and tear on the compressor and the other parts, right? Which really contribute to the durability and longevity of the system. And it's why we're able to offer a 12-year warranty on many of our products. So I got a couple of questions here. So Brody's asking about cost differences between these systems, right? We've done a lot of comparisons between a single speed system and an inverter driven system. It's hard for me to articulate that really clearly. It's going to depend on market dynamics. It's going to depend on contractor pricing. From a pure equipment perspective, the cost for adding an inverter isn't really incredible. A lot of the benefits that we're talking about do require communication between all of the equipment, because it is more complex, because there's multiple sensors, we're reading in more data. So from an install perspective, it can be more complicated to make sure that the systems are wired appropriately, that you have the right electrical in certain places. So there certainly is a cost premium. It's hard for me to really put a close number on that. I've got a question from Pace, who's asking if the Sky Air will work in a dual fuel approach. So as configured today, the Sky Air is not compatible with, let's say, for example, a gas furnace. It is a centrally ducted product, but it is not compatible and cannot be attached on top of a gas furnace. There are two other systems that I suggest you explore if you're interested in dual fuel applications. One would be the Daikin Fit heat pump and or the VRV Life. You could explore both of those products. They kind of serve different needs in different markets, but those could be good options for you if you're thinking about adding a heat pump to an existing furnace. If you're asking more of like, this probably wasn't your question because you were asking about Sky Air, but the ductless product, the Aurora, to some degree can be dual fuel. We have integrated controls. So if you've got like a hydronic heating system and you've got a good contractor that understands how to leverage the control, specifically our controller Daikin One Plus, you can achieve some dual fuel capability there and kind of integrate the controls of those two systems. Kyra's asking about adding inverter to the compressor of a heat pump water heater. I think at the end of the day, I'd suggest it depends. There in North America today, most residential heat pump water heaters are kind of the integrated hybrid type, where they're not exchanging temperature with the outdoor, but are capturing heat from maybe an unconditioned space or somewhere else within the building envelope and putting it into the heat. I can't speak to those systems specifically. It's just not my area of expertise, but what I can tell you is Daikin does sell and offer heat pump water heaters in other markets that are split systems. So they operate a lot like an air source heat pump, where they're actually capturing air from the outside. They're actually capturing heat from the outside and injecting it into a water tank, right? For all of those products across the globe are using inverters. So, for us, I think it makes sense. I don't think that most of the hybrid water heater solutions that are used in North America for single family buildings are using inverters. And unfortunately, I can't tell you whether it really makes sense or not. I'm going to move on. I'm going to show some examples. We've got a couple of minutes left. Please keep the questions coming in. So I want to go over a couple of examples of like what this looks like in the real world. Basically, Daikin has gone through this kind of general or rough field study to try to really articulate and demonstrate some of the benefits. And I realize the slide I'm showing here is Florida. As I kind of go through these, we'll get closer to the climate that we're most interested in. But really what we've done is we've taken a very similar systems. These are centrally ducted either heat pumps or ACs, and we've installed them in different homes. The homes are very similar, if not identical, probably built in the same year, probably the same layout. They do have different occupants in them, so we're not controlling everything, so they could be used differently. But basically what we've done, we've taken a 16 SEER, for this example, both products are 16 SEER. One has an inverter and one does not. And we've monitored the energy consumption, right? And this is kind of a simple way to try to demonstrate some of the real world benefits on a pretty big scale in a couple of different climates, right? So this example is in Florida. It is for a heat pump. And looking at the graphics below, and we're going to go through a number of examples of these across the country as we kind of wind down on time. The yellowish line is going to be for the non-inverter system, 16 SEER, so it's the same efficiency rating. And then the darker, more orange bars are going to be for the inverter product, right? What you can see, there's a couple of observations here, and they're going to be pretty consistent as we go through these, right? And again, I hope this is a little repetitive, but just to drive the point home, the non-inverter system, that power consumption is roughly fixed. You see it's either off or it's consuming about 3 kilowatts of energy, right? For the inverter product, what you see is a lot more variability. For this particular application, sometimes it's operating at 1 kW, other times it's operating at 2 or even all the way up to 5, right? So we've got modulation, we've got the ability to vary the capacity of the heat pump, but really what I think is important to call out, for the most part, looking at this data, we can see that for most of these bars, the power consumption of the inverter product, which supposedly has the same efficiency, is significantly lower. So it's operating at a much better efficiency level. And as I suggested earlier, right, those seasonal efficiency metrics like SEER, they really don't do a great job of differentiating the efficiency of an inverter product versus inverter product. And we've got a couple of examples to show that here. So same thing, different location. This is Louisiana heat pump, same systems, one inverter, one non-inverter. And the graphs are showing the same thing. We've got modulation in the inverter product, much less variability in the energy consumption of the non-inverter product. I think the previous example for Florida is roughly 34-35% energy savings. For this example, it's 31% energy savings in Louisiana. I see a couple of questions really quickly. I see Susan asking about savings per month, per year. Really, it's going to depend on each application and what what you're kind of comparing it to the baseline, right? I think for the most part, for similarly rated systems, right? For this example, we're talking about 16 SEER. You'll see as we go through these, the savings are generally in the range of 20 to 30%, right? So if a customer is using, spending $2,000 over the year, 20% conservatively, $400 a year. Just to do some real quick math. So we're looking at an example for South Carolina. This one's on the lower end, right? It's 20% savings. But again, I think the findings are very similar. So this is in New York. We're getting closer to home. This is an air conditioner, but we're seeing roughly 20% savings. And again, the same thing over and over and over here. Non-inverter system isn't modulating. It's turning on, it's turning off, and it is less efficient because of that. It can't modulate. And lastly, we've got Ontario. You know, this is a air conditioner system, and this is on the higher end of savings, 31%, right? So again, you know, I think if you're just looking at the impacts of an inverter, right? I think thinking about, you know, an additional benefit in the 20 to 30% range for a similarly rated piece of equipment is kind of what the data is showing here. So I hope that was helpful. I hope it was interesting. I hope it wasn't too complex. I hope y'all learned so much. So I've got a bunch of questions here. I'm going to try to go back and try to make sure I don't miss any. So bear with me a moment. Keep the questions coming because we got you know, 7 or 8 minutes here. Susan asked a question about our air conditioner manufacturers looking to use inverter technology, and I think the answer is absolutely yes. You know, I'd suggest Daikin is a little unique in the sense that we really feel strongly that inverter should be kind of like the bare minimum, as I think it was John suggested earlier, like require inverters. I won't say that Daikin, almost all of the systems that is sold under the Daikin brand have an inverter, right? We feel strongly that that is the right approach to providing comfort. I would also suggest a lot of other manufacturers do have a solution that includes inverter, right? So most aren't ignoring the technology. I think the difference is just how strongly we feel compelled that, you know, all solutions should have it, or, you know, just the highest tier and the highest class. Someone's asking about how can we install HVAC that will never leak or adopt a refrigerant standard with minimum GHG potential. I am going to defer to my colleagues presenting on refrigerant on September 15th at BuildingEnergy NYC. It's a really good question. I am sure that that will be a better venue to ask that. My quick take, I don't totally want to ignore your question, is that I think through you know, better training and through new techniques, we can get much closer to split systems that never leak. Right? I don't know if we'll ever get to 100% leak-proof systems, but I think as an industry, everyone can do a little bit better, and that certainly will be talked about at the sessions on September 15th in person. And, you know, certainly the industry is moving towards lower global warming potential refrigerants. So I will let my colleagues talk about that in more detail next week. Eric, I hope you plan on attending in person. I do have my contact information here, so if you want to kind of connect and talk more about that, feel free to reach out. Jean is asking about, or kind of stating that I've shown some examples that show that SEER is not a reliable predictor of energy use for inverter products for a cooling season. Yeah, I think that's a really reasonable takeaway from the information that I've shared. I would suggest, you know, I can't speak for others, but I think broadly a lot of folks that are concerned about efficiency, that look at the detailed data that comes from these systems, I think many people are reaching that same conclusion today. Someone's asking me about an ASTM spec, and sorry, Charlie, that is not my area of expertise, so I can't address that. Gene's talking about R32 still being too high for too high a GWP. Again, I think all these topics will be covered on Thursday. Thank you for the questions and the comments. I think I think Ben will share, Pace is asking about sharing the slides. I will share these with Ben and he will post them to the website where the recording will be posted, so you will have access to these. John's linked to a better presentation of refrigerants in YouTube, so thanks for that. Oh, this is great discussion, guys and gals. Thank you so much. Seeing a lot of discussion. Is there any quantification of what inverters were due to peak load on the grid? Really interesting question, Dan. I don't know if anyone's looked at just inverters, right? I think there could be a lot in that question. But I think the reality is a lot of people are looking at what are the impacts of more heat pumps being used for heating and what that impact would do to the electric grid, right? As I've kind of tried to show here, I think my point is that inverters allow us to use heat pumps when it's cold out. So, when it's 10 or 5 degrees out, we can now use heat pumps for heating year round. That is really unlocking the opportunity for us to use heat pumps around the year in New York and New England for heating. To the extent that many people use heat pumps, it can change our electric systems from a summer peaking system today to winter peaking in the future, right? And I think that's the real concern. How do we minimize that? And most of the folks in the space are focusing on efficiency at 5F as kind of the line in the sand to try to minimize those impacts. And I think as an industry, we'll continue to work with utilities and program administrators to make sure that we're providing a systems that operate as efficiently as possible when it's cold out to minimize those impacts. Ben's answering some of my questions here that I've already answered. So sorry to repeat. John's asking if what's required for heat pumps to qualify for the new IRA incentives. It's a good question. So I've talked about NEEP a little bit as part of this presentation. We're running low on time, so I'm going to keep my answer really short. I'm going to give it back to Ben. If I wasn't able to answer your question, I will try to answer them in writing, and hopefully maybe those can be posted to the website too. But for the IRA, generally that's referencing either CEE Tier 2 or Energy Star as a prerequisite for heat pumps to qualify. So, I think it's an interesting question. Energy Star does have a specific carve out for cold climate heat pumps. So I think a lot of the work that NEEP has done and a lot of those heat pumps hopefully will qualify for those IRA programs. On that time, I had a lot of fun. I hope. I want to thank you all for spending the hour with me. I think this was really really engaging, great discussion, and I want to thank Nessie for allowing me to host this. And if you are planning to attend Building NYC, I will certainly be there. Please come and say hello. Let me know what questions aren't answered. If you want to talk, I'd be more than happy to engage, and I hope to see you all there. Ben, I'm going to hand it back to you to close it out. Thanks, everybody.
Thank you, John, and thank you to Daikin for supporting Nessie and the Building Energy NYC conference. This has been a great session today, and we look forward to seeing many of you in person on Thursday next week. Make sure to register by Monday at 5 p.m. For advanced pricing. And as John said, the video of this and the slides will be posted on the session page. You'll all get a follow-up email with the link to that as well.